As you can clearly see, our wave is moving from the west to the east. And as it is moving from the west to the east, the particles in our medium is also moving west to east. One, two. So we are going to zoom in on the longitudinal wave so you can see what I'm talking about. There's something interesting I want to show you. In front of us, we still have a longitudinal wave, but take a look at this. Okay, we can see that our wave is moving from the west to the east, if so we can say. But let's pay attention to this red particle. Take a look at it. It moves backwards, it moves forward, and then again it moves backwards. So that's the movement of particles in a longitudinal wave. They move parallel to the direction of the motion, unlike in transverse where they are moving perpendicular. Here they move parallel to the motion of the wave. But the position of the particles, they just move to the east and move back to the west. They don't move with the wave and never come back, as we can clearly see. It might look like that if you're not paying much attention. But if you pay attention, you can clearly see that the particles move to the east, move back to the west, east, west, as the wave propagates through the medium. So that is longitudinal wave. By definition, a longitudinal wave is a wave where the particles of the medium vibrate parallel to the direction of motion of the wave. But what do we call this region where particles are close to each other? And this region here where they're not closely packed. A compression is a region of high pressure in a longitudinal wave, while a rarefaction is a region of low pressure in a longitudinal wave. You can clearly see that these points where, or the region rather, where the particles are close to each other, we call that a compression. It's a region of high pressure, while a region of low pressure is referred to as a rarefaction, clearly indicated on our sketch. So those are some of the properties of a longitudinal wave. The same wave equation we were using with transverse wave also applies to longitudinal waves. The speed is still equals to the frequency multiplied by the wave length. A good example of a longitudinal wave is sound wave, and we are going to talk about that next. So let's go ahead and take a look. So a sound wave is an example of a longitudinal wave, as I have stated, and then vibrations in a medium in the direction of propagation create sound wave. Sound waves cannot be propagated in a vacuum. So that is the second point. That is the second thing you need to note. Speed of sounds depend on the properties of a medium. It travels faster in a medium with particles closely packed. In a solid, the speed of sound will be greater than in a liquid, and then the speed of sound in a liquid will be greater than that in a gas, because as the particles become more closely packed, the speed of sound increases. Sound waves travel faster through liquids like water than through the air because the water is denser than air. Sound waves travel faster through liquids like water than through the air because water is denser than air, obviously. And this is just another example to show that in liquids, we expect sound to travel faster than in air because the particles in a liquid are more closely packed compared to the particles in a gas. The last point, sound waves travel faster in solid than in liquid because a solid is denser than a liquid. Again, making emphasis on the relationship between speed of sound and how closely packed the particles in a medium are. The more closely packed they are, the faster the speed of sound. Characteristics of sound. The first thing we look at is the pitch. The frequency of a sound wave is what your ear understands as pitch. So if the frequency is higher, we're going to have a higher pitch. So what are we saying? We're saying that frequency is directly proportional to the pitch. As the frequency increases, the pitch increases.
Hopefully you can hear that the pitch in my voice has increased, because now I'm trying to talk very fast, and this is how frequency affects the pitch. So I've increased the frequency in my sound waves, and your ear is interpreting it as an increase in the pitch. So this is the relationship between frequency and the pitch. As the frequency increases, the pitch increases. Right, let's move to loudness.
The amplitude of a sound wave determines its loudness or volume. Loudness is the listener's evaluation of amplitude. A larger amplitude means a louder sound. Loudness is directly proportional to the amplitude. Loudness is measured in decibels. I'm sure you've seen this unit in electronic devices. That is the unit for loudness, decibels. Let's consolidate. We're saying that the amplitude is related to the loudness. When I talk like this, I sound louder because I have increased the amplitude of the waves I'm emitting. So this is what we mean when we say the amplitude affects the loudness. Hopefully that makes sense. Now let's talk about the tone. The tone is a measure of the quality of the sound wave. Let's go ahead and see if we understand pitch, loudness, and tone. Okay, so we have an example here. Two musical notes have the same amplitude. So amplitude is related to what? Amplitude is related to loudness, like we've talked about. But note A has twice the frequency of note B. Okay, frequency is related to pitch. In which respects will A, the sounds differ? These two notes have different frequencies, so the pitch is going to be different. The pitch of the two musical notes will be different. And then B, in which respects will their sounds be the same? They're going to be the same in terms of loudness because we have the same amplitude. So amplitude, loudness, frequency, pitch. This is a type of question you would usually expect in a multiple choice. So let's make sure that we familiarize ourselves with the characteristics of sound waves: pitch, loudness, and tone. Let's move to the following aspect. If you were to stand in an empty room with no furniture and say, hey, you would hear a follow-up saying, hey, 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 something like that, right? So that is echo. Echo is when a sound wave strikes a wall or any hard surface and is reflected back and you hear it again. So that is why in an empty room you will hear echoes. When you say something, you will hear repetition of that same thing. It's because the sound waves hit a hard surface and then they bounce back, come back to your ear, and you hear it again. But in a room with furniture, there's a lot of soft materials. For instance, if you are in a living room, there's probably a couch. What else? Other soft materials. So when the sound waves strike the couch, they don't get reflected back as they would in a normal wall. So that is echo. Echoes are a result of the sound waves hitting a hard surface and being reflected back, and you hear them again. Our last aspect, let's take a look at ultrasound. So ultrasound is sound with a frequency that is higher than 20,000 hertz or 20 kilohertz. This is sound we cannot hear with the human ear because our range, the top of our range is 20,000 hertz. When sound is of a frequency beyond 20,000 hertz, then we cannot process that sound as humans. Right. And then the most common uses of ultrasound is to create images. The use of ultrasound to create images is based on the reflection and transmission of a wave at a boundary. When an ultrasound wave travels inside an object that is made up of different materials, part of the wave is reflected and part of it is transmitted. The reflected rays are detected and used to construct an image of the object. So that is ultrasound. And lastly, let's talk about the use of ultrasound in medicine and in the industry. So in medicine, We use it to visualize muscle and soft tissue. An example of that is during pregnancy, right? That thing they use there on the belly of the woman to see the fetus, depending on which stage of development, is ultrasound. And then lastly, to generate local heating in biological tissue, e.g., to break up kidney stones. So, well, apparently they use ultrasound to break kidney stones. I don't know much about that, but there we go. And then in the industry, ultrasonic cleaners are used to clean jewelry, lenses, and other optical parts, watches, dental instruments, surgical instruments, and industrial parts. Well, that is the use of ultrasound in medicine and in the industry. So now that we have covered all the basics, let's go ahead and solve some past exam questions.